lecture of this course. Let me remind you that in the first lectures we defined ETH and SETH, exponential time hypothesis and its strong version, which roughly speaking say that SAT cannot be solved in sub-exponential time, or that general SAT cannot be solved in fewer than 2 to the n steps. And today in 2 lectures we are going to be using these conjectures to prove exponential and slightly super exponential lower bounds for other important problems. In the first lecture today we'll prove hardness of different graph embedding problems under the ETH assumption. All right. So let me first define the graph homomorphism problem. In the graph homomorphism problem, you are given 2 graphs, G and H. We'll be using, the number of vertices in the graph G will denote by n, and the number of vertices in the graph H will denote by little h. And in this problem, you want to check if there is a homomorphism from G to H. Homomorphism is such a mapping that each edge of G must be mapped to an edge of H. There are no other restrictions. Like non-edge can be mapped to an edge, that's fine. But every edge must be mapped to an edge. Moreover, several vertices can be mapped to one vertex. That's also good. Let me show you an example. Oh, yeah, I forgot to say again, please ask questions during the talk. And again, if you don't feel like asking questions in English, you can ask in Russian. I'll try to translate. Right. Right, and moreover, we'll be talking about subgraph isomorphisms in 5 minutes, yeah. So here's an example. Say this is our graph G, this is graph H. Is there a homomorphism from this graph to this one? Yes, you can actually map all these red vertices to this red one, all these blue ones to the blue one, and all the green ones to this green one. And to check that this is actually homomorphism, you want to say that every edge is mapped to an edge. For this, we'll note that all edges here connect vertices of different colors. And here, for every pair of different colors, I do have an edge there. So this is a valid homomorphism.
So can we say that every three-color graph is a homomorphism to a triangle?
Correct. Moreover, we can say that if this right graph H is a triangle, then the problem is exactly 3 coloring.
But 3-color graph may not have any edges, and when we apply homomorphism, we will get graph of 3 vertices without edges.
You can still find a homomorphism from this graph to an empty graph. Homomorphisms is a mapping such that every edge is mapped to an edge. A non-edge can be mapped either to an edge or non-edge. Yes? Right. And if the right graph is fixed to be a triangle, then this is exactly the 3-coloring problem. Do you see what will happen if I say have here a clique of size k? Clique is a full graph, full undirected graph on k vertices. This is exactly k-coloring problem. So k-coloring problem is a special case of graph homomorphism problem. This problem is more general. Okay, so what do we know about this graph homomorphism problem? Again, by n we denote the number of vertices of this graph on the left, by h the number of vertices of this graph on the right. What's the trivial solution to this problem? How fast can you solve it? Sorry? Simple brute force. Yeah, what's the running time of such an algorithm? Yeah, so you have h vertices on the right, and they are going to be images of your n vertices on the left. So one way to do brute force is just for every vertex here, try all possibilities here. So the question is, maybe it suffices to brute force only partitions. I think not necessarily, because several vertices can be mapped to one in the graph homomorphism problem. Right, but
for different partitional and construct the mapping.
yeah, right. So one way to go over like all partitions into H groups is just to try each of these images for each of these vertices, right? Yeah. So this will take time H to the n just to construct all the partitions. And then in polynomial time, you just check whether an edge, every edge is mapped to an edge. So in particular, we can solve this in time roughly H to the n, up to like polynomial factors, which we again ignore. I'll be using this notation, 2 to the n log h later on. And yeah, also important thing in this talk will be talking about graph homomorphism where the right graph H can be of arbitrary size. You'll see in a moment that it's important whether it's larger or smaller than the left graph, but in our case, we allow H to be any function of n. So you shouldn't think that H is necessarily like a fixed constant graph or something like this. It can be a graph of any size as a function of n as well. Okay, and whatever H and n you have, you can always solve it by brute force in time roughly 2 to the n log h. Right, but you can actually check it in polynomial time, right? You can check that every edge is mapped to an edge, and I said that we're going to be ignoring polynomial factors.
Well, log h is also polynomial factor then?
It's like, it's multiplied in the exponent. It's not like polynomial anymore, right? It's not like times 2 to the log h, yeah. Any other questions? Those are amazing questions so far. Okay. So a natural question is, can we actually do better? Like we know this problem is NP hard because, for example, it's more general than 3 coloring, we just saw it. So probably in the nearest future we won't find a polynomial time algorithm. It's an NP complete, yeah. You can, since we know it's NP complete, we don't expect a polynomial time algorithm for this problem to be found soon. But it doesn't mean that we can beat such a huge, slightly even like not quite exponential function. And today we'll sketch the argument which says that under the weak ETH assumption, there is no algorithm which solves it like asymptotically faster. Asymptotics is going to be in the exponent here. Any questions? So we'll say that essentially brute force is like almost close to optimal under the ETH assumption. Questions?
It's not clear. So the claim is that for every H or something like that?
Actually, for every H, like from 3 to whatever function of n you want, there is no algorithm. Yeah, okay, let me say that when H is equal to 1 or 2, the problem is trivial. When H is 1, then it's just clear, right? You want to map a graph to one vertex. You cannot map this pair to one vertex because edge must be mapped to an edge. So there is a homomorphism to a graph of size 1 if and only if your graph on the left-hand side is empty. What about a homomorphism to a graph on 2 vertices? If there are no edges, then clear again, your graph must be empty. If there is an edge, then what graphs can you map there? Bipartite graphs, right? So if you can partition your vertices such that all edges go only between 2 parts, then you map all these vertices here, all these vertices there, and every edge is mapped to an edge. On the other hand, if you did find a mapping here, then you have a bipartition. So such a graph, such a mapping exists if and only if G is bipartite. And this problem is solvable in polynomial time. But once H is at least 3, it's an NP-hard problem, as we saw, in particular, generalizes 3 coloring. And for every H, which is a function of n, and which is at least 3, we prove that your running time must be at least 2 to the n log h, some constant in the exponent. H is a function of n. H can be like log n or 2n. It's arbitrary function, like efficiently exponential time computable function of n, which is always at least 3. Yeah. Yeah. Right. Yeah. This constant. Yeah. This is a terrible constant. Yeah. And not only it's like as bad as you have in specification lemma, we also like multiply, like divided by 500 or so in our reductions. Yeah, it's terrible constant. And yeah, of course, this constant is in the exponent, so it matters. But at least we know that asymptotically, when we talk about like exponent here, brute force is optimal. Other questions? The question is it true that there are no algorithms which would solve this problem faster? I mean, they might exist, but then they would break ETH. They would solve k-sat in sub-exponential time. So you should think of it, like one way of thinking about this is that if you want to break ETH, if you want to find efficient algorithms for SAT, then one way of doing it is to solve graph homomorphism problem. Yeah.
It is not evident to me. I'm just curious about what is the hardness of the problem if we have graph H without cycles. It could be, for example, 3 vertices and 2 edges. Is it also hard?
Yeah, like problems without, I mean, if the graph H doesn't have cycles, these problems are also hard, and we'll see it in the last section of the talk. Yeah. All right. Good. Let me show you one more example. Assume my left graph is much smaller than the right one. In this case, the left graph is just a triangle. And the right graph is a huge graph on H vertices. Is there a homomorphism from this graph triangle to this one? Yeah, of course, I can map this triangle to this triangle. And moreover, if I map a triangle to anything, then this must be a triangle as well, because each edge must go to an edge. These two vertices can never be mapped to the same one, because there must be an edge between them. So every triangle must be mapped to a triangle. Is it clear? We assume like the right-hand side graph never has self-loops, because once you have one self-loop, you just map all the graph, whatever graph you have, to this self-loop. It connects all the vertices. So I assume it never has self-loops. In this case, a triangle, every connected pair must be mapped to a connected pair. So a triangle must be mapped to a triangle. But this way we found it like a triangle in a graph, which is kind of interesting question. Now assume instead of a triangle, I have a clique of size k here. Then what problem do I have? Yeah, it must, exactly, yeah, clique problem. Yeah, it must be the case that this clique on k vertices is mapped to a clique on k vertices. In particular, I just found a clique in this graph on h vertices. So if my left graph is smaller than the right one, then in particular I can solve the clique problem, which is also an NP-hard problem. So this problem, graph homomorphism, generalizes both of them, coloring and clique. Key coloring and key clique. Yeah. Questions about this?
And if you have a square instance triangle, then we are sufficient with just one edge.
If here you have square, yeah, it's a bipartite graph, and we saw that every bipartite graph can be mapped to an edge. Yeah. Okay, so this is one setting of graph homomorphism problem when the right graph H is larger than left graph N. The other one we already saw generalized coloring. In this case, like usually the left graph is larger than the right one. And this is actually two different settings. Let me show you the hierarchy of these problems. There is a very general problem called two constraint satisfiability problem. It's a very general problem and generalizes even graph homomorphism. And it also has two graphs of size n and h. And what we know about and we just saw that coloring and click are two different special cases of homomorphisms. In this one, like left graph is larger and this right graph is larger. So what do we know about algorithmic complexity of these problems? We know that coloring, any k coloring can be solved in time just 2 to the n. And just like plain exponential time, we call it. Plain means this exponent is just linear, without any logs or without any superlinear functions. Sorry? No, actually it doesn't. You can even find the chromatic number in time 2 to the n. It's not that trivial. It was discovered like 7 years ago or so. Yeah, but you can solve any k coloring even if 1k is a function of n in time 2 to the n. Times poly as always, yeah. Right, right. On the other hand, for this super general problem, we know a lower bound of 2 to the n log h under the exponential time hypothesis. Again, I'm ignoring this constants here in the exponent. N is the number of variables and h is the size of the alphabet there. It is slightly more general than, no, it is like significantly probably even more general than homomorphism. And on the other hand, for the click problem, which is a special case of homomorphism, where one graph, the right graph h is larger than n, here under the ETH we do know superlinear lower bound, but it only holds for very large h. In general, in click, h is larger than n, and for this lower bound, you need it even like significantly larger. So now the question is, what the actual complexity of the homomorphism problem? I mean, it still can be the case that for most values of h, it's in time 2 to the n, and I assume that most people did actually believe that it's closer to coloring. That for most values of h, for example, for constant h. You can solve it in time 2 to the n independent of h, or like c to the n independent of h.
So can I ask about the click? I should understand it. So what you've just said is h, we know this lower bound for the case when h is larger than n?
And significantly larger, yeah.
Which is, I mean, n is the size of the left graph?
Right.
Oh, n is the size, okay, n is the size of the click.
H is, in our setting, h is a function of n, and here by large h, I mean it's a large function of n. Oh, no, like in click in general, you have h larger than n. In so click problem. Here, it's not just greater than n, it must be at least like n log n. Probably little omega of n log n.
So you're looking for a click of size n?
In a graph of size h. Yeah, so h is like a priori is greater than n, but here for this lower bound you need even stronger guarantees. So in some special case we do know such a lower bound, but it's a kind of very special case. H is a function of n. Here I mean h is a large function of n. For example, superlinear.
So it means that click should be sublinear.
Right, yeah. No, of n log n. So you're looking for click of size less than n over log n. Yeah. Okay, so we know that in some special case we can prove super exponential lower bound, but the question is, what about the general graph homomorphism question? Like many people believe that for constant h you can solve it in time c to the n independent of h, while c does not depend on h. And this work will say that actually no, the lower bound is 2 to the n log h, that homomorphism is significantly harder than coloring and some other special cases. It's closer to this general problem. And this is based on our joint work with Marek Tsigan, Arkadiusz Sakala, Jakub Pachotsky, and 3 people which are present at the school: Sasha Kulikov, Vanya Mikhailan, and Fedya Fomin. All right, so we want to prove this lower bound for the graph homomorphism problem. Is there problem clear? Good. Let me show you a similar problem. I guess I already got a question about it. Subgraph isomorphism problem. Which is isomorphic to G. This just means that you can delete vertices and edges from H, and you want to see the graph G after this. This is what subgraph isomorphism is. You can be removing edges and vertices when I see G. And this problem is also nice. We saw that here we generalize Hamiltonian cycle, bandwidth triangle, like a bunch of important problems as well. Let me show you an example. Say I want to check if there is a subgraph isomorphism from here to this host graph. This means in this graph, I want to remove vertices and edges and see a cycle on 7 vertices. But this graph also has 7 vertices. What does it mean to... this means I cannot remove vertices, right? Because I want to see a graph on 7 vertices as well. So I have to be removing edges. And I want to, after this, see a cycle. The question is, can we be removing only vertices and edges adjacent to them, or like arbitrary edges? You can just, like, for example, remove this edge without removing any vertices. Right, so when here we have a graph like a cycle on n vertices, here we have arbitrary graph on n vertices, then we see that we have to be removing edges in order to get a cycle which corresponds to the Hamiltonian cycle problem, right? In particular, this problem generalizes Hamiltonian cycle, which is also a very hard, an NP-hard problem.
So, more or less, this is the same as a homomorphism, but the number of your image should have the same number of vertices, right?
Not necessarily. Here, 2 graphs can also be of different sizes. Not necessarily. Your image must be of this size, yeah. Your image of graph on n vertices must contain exactly n vertices, yes. Then it is go, yeah. And we will use exactly this observation to prove hardness of this problem, yeah. Any other questions? Good. So the main results of this work are that under the ETH assumption, there is no like significantly faster than brute force algorithm for the graph homomorphism problem, and there is no significantly faster algorithm for subgraph isomorphism either. Right? Yeah.
Can we go please to the previous slide?
This one?
Yes. Why can't we merge 2 independent vertices of a cycle?
Yeah. Why can't you map this and this vertices to one? Yeah, this is not graph homomorphism problem. This is subgraph isomorphism, which says you want to remove vertices and edges. Image of a graph on n vertices must contain exactly n vertices. Yeah. Yeah. Yeah, that's fine. We also prove, like here you can see that actually we prove a general lower bound, and it matches a brute force algorithm for this problem as well. But it's probably easier to think in the case of subgraph isomorphism about 2 graphs of size n. This is still like very hard problem. Right, we do. Okay, now the last piece, the last definition for this talk is the least homomorphism problem, which is just a technical definition which will be needed for our proofs. So we know homomorphism question. It's like question where you don't have this like weird edges. Just do have a homomorphism from this graph to this graph. And sometimes I want to be saying that do have a mapping from this graph to this graph such that this vertex is not mapped here. And this one is not mapped here. And this one is not mapped here. So for each vertex, I want to give you a list of allowed vertices. Or maybe a list of prohibited vertices. It's the same. Yeah. Can you still find a homomorphism? In this case, you can. You see that, again, I want to map these red vertices to the red one, blue to the blue one, green to the green one. And this one is not mapped to the red, this one is not mapped to the blue, this one is not mapped to the blue. So I did find a least homomorphism for this problem. Okay, and now in order to prove lower bound, we'll go through a bunch of reductions. So we start with SAT. We know like ETH talks about hardness of the satisfiability problem. Then we say that 3 coloring is hard. Then we reduce it to least homomorphism, to homomorphism, and to subgraph isomorphism. And this way we prove that, for example, these two problems are hard. And here, like each reduction uses like different techniques. Here, this is basically a sparsification lemma kind of things. This is a gadget-based reduction. This is a cute combinatorial like argument, and this one is just like a bunch of calculations, very simple ones. We'll see some of these reductions in the remaining 20 minutes. Any questions so far? This is the plan. We start with SAT, reduce it to our problems, means our problems are hard. Just like in the case of proving NP hardness, we just show polynomial time reductions. Here we want to take the parameters so that we can prove exponential or super exponential lower bounds. This seems like a restriction. Yes, it is, but we also have more freedom in the sense that in normal NP hardness reduction, your reduction must take polynomial time. Here, I'm proving a super exponential lower bound. I'm allowed to use, say, exponential time reductions. We'll see it in a minute. I'll explain it once we get to there. It's like in 5 minutes. Yeah. Okay, so let's start with this reduction, SAT to 3 coloring. Yesterday in the problem solving session, we proved that under the ETH assumption, 3 coloring on n vertex graphs of average degree 4 requires time exponential in n. Yeah, but we actually need maximum degree, which I didn't realize yesterday. And we just like will quickly fix it. So yesterday we proved that for average degree, it does require exponential time. Now let's reduce it to the maximum degree. So I have a graph where some vertices have degree higher than 4. I want to reduce their degrees. For this, I will be using some gadgets. And the idea of the gadget is, assume I have a vertex of degree, say, maybe 4. Then I want to split it into 2 vertices, but I want to make sure that these 2 vertices will be colored the same color.
And degree 4 is okay.
Yeah, this is just an example. It's not actual proof. How could I do this? I would take one vertex, another one, and do probably the following thing. And then I'll say this and these ones are like sockets. They form a splitting of this vertex. So that if this one is colored in color 1, then these 2 must be colored in 2 and 3, which gives me the same color here. So instead of having one vertex of degree 4, I have this gadget. Each vertex has like degree 2 so far, and again, I can draw these 2 neighbors here and these 2 neighbors here. It didn't help me here, this is a 2 example, because I still have degree 4, I didn't reduce it. But now we'll see how to actually do it for degrees greater than 4. Does it make sense? I just want to split one vertex into a couple ones with the guarantee that they all are colored the same color. Okay, so probably like this. I want to say that once I have a vertex of degree sorry, should be a different one. Let's call this gadget H3. It has 3 sockets. And again, sockets will correspond to the degree of our graph. And here I want to say, again, I have this guarantee if one socket is colored color 1, then 2 others must be colored color 1 as well. It's easy to verify by the same argument. Just assume this is 1, then these 2 must be 2 and 3. This must be 1 again. These 2 must be 2 and 3. This must be 1 again. And so this one must be 1 again. And now for high degree vertices, I just combine a bunch of such gadgets. Why not?
You can color both. You have 2 vertices on the top, and you can color them by 3.
These 2?
No, because
Okay, assume these 2 are colored 3. Then, not these ones. Which ones?
this one and one to the right. So this one.
This one and
One to the right.
like this one.
Yes. So color.
Yeah, assume this and this are colored 3. Then this must be colored 2. This must be 1. And what is the color of this vertex then? Yeah, okay. So in case of higher degree, I just combine a bunch of such gadgets. And again, I have sockets here, 1, 2, 3, 4, 5. And I have the same guarantee again. Like if this is colored 1, we already saw this is 1, this is 1. Then by the same argument, this is 1, this is 1, this is 1, this is 1. So in particular, all the sockets are colored 1. And note that degree of every vertex here is at most 4. And each socket has degree only 2. So once I have a large degree vertex, I just draw such a gadget and split its neighbors into the sockets. Does it make sense? This way I get a graph of maximum degree 4. And I introduce just a few vertices. If I know that my average degree is 4, then I don't need to reduce the degree too often. It's like half of the vertices have degree 5, half have degree 3, and I need those gadgets for vertices with degree 5. Okay, did I convince you that the coloring problem is hard even, 3 coloring even on graphs of degree 4? Sorry? Assuming the average case, but yesterday in the problems solving session, we proved that average case actually does require exponential type. Okay, so that was actually the first step, yeah. We reduced SAT to 3 coloring, and that's it. We just used the sparsification lemma and a couple of standard reduction for NP hardness. Now, to confuse you even more, I will show you the last reduction first, from homomorphism to subgraph isomorphism. Okay, this is exactly a simple argument that Vanya already mentioned. With the one exception that Here, I want to reduce homomorphisms to 2 to the n copies of the subgraph isomorphism problem. Note that when I'm proving NP hardness of some problem, this reduction is just useless because like reduction must run in polynomial time. Here in time 2 to the n you can solve like half of the NP hard problems. It's not fair. But I'm proving 2 to the say n log n lower bound for these problems. If in my reduction I spend time 2 to the n, this is all right. This doesn't hurt me. Okay, I'm going to reduce it to subgraph isomorphism problem on 2 graphs, G1 and H1, and they both will have the same number of vertices as the left-hand side graph in the homomorphism problem. How do we do this? That's exactly what Vanya said. Assume there is a homomorphism from G to H. Then each vertex in H has a bunch of preimages. Maybe 0, maybe like 15 or something. It has some number of preimages. Now, let's just try to guess how many preimages each vertex of H has. For this, we'll need from these n vertices, with repetitions, we want to choose H1s. So this is combinations with repetitions, and there is this like simple formula for it which reduces to normal combinations. It says that the number of the things is at most n plus h minus 1, choose h minus 1. If you wanna, again, if you wanna choose from n vertices, if you wanna split them into and in particular, this is less than, as any binomial coefficient is less than 2 to the power of the top coefficient, is less than 2 to the n. We defined n, if you remember, as just the sum of these two things. So there are at most like 2 to the n such sequences. And also we can efficiently enumerate them. We basically go and enumerate all combinations. This is easy. Any questions? So far we guessed for every vertex how many of H, how many preimages it has. If there exists a homomorphism, yeah. Now we're almost done. Assume we guessed like one sequence. Now we create an instance of subgraph isomorphism where the left graph is the same as the left graph in homomorphism, but in the right graph you just replicate each vertex this many times. You get okay, so once we guessed the sequence correctly, yeah, there is a subgraph isomorphism as well. So now the whole reduction is the following. Go through all 2 to the n sequences and check if there exists a subgraph isomorphism. If there exists a subgraph isomorphism for at least one such sequence, then there was a graph homomorphism for the original problem. Otherwise, there was no such homomorphism. Is it clear? Yeah.
You mean when you replicate vertices, you connect them somehow with other replications?
Yeah. By replication, I just mean, yeah, each vertex, they're connected in like the same way as they were connected in the original graph. That is, assume UV, can you see what I'm writing here? Or should I take the different marker? I just don't see the, can you see it? If UV was an H in H, then every copy of U is connected to every copy of V. Okay, that's what I mean by replication here. Any other questions?
Can you show various slides?
Yeah. Yeah.
Are you sure there is most resistance? If VH and VG and VH equal, then it seems
If what? If VG and VH equal?
equal.
Yeah.
Then it should be less than 2 to the n.
It should be less than 2 to the n, right? Oh, it shouldn't, you're saying?
It should be less than 2 power 2n.
That's correct, because n, we define n as a sum of these two things.
Ah, okay.
You're right that it should be like 2 to the 2 number of vertices of G. Yeah. All right.
Back to my previous point, if G is much smaller than H,
Right.
then you add nodes.
Like subgraph isomorphism doesn't quite make sense when G is much smaller than H. Because every vertex must be mapped to its own vertex. So you must have, in the host graph, you must have at least that many vertices.
So G is smaller than H. That's the problem. G is the
Oh, when G is, sorry, yeah. Yeah, so what?
so if G roughly the same hardness.
That's right. But when you want to prove hardness of subgraph isomorphisms for graph with different sizes, then you also blow one of these graphs, like you blow H by like dummy vertices. The brute force algorithm though. Yeah.
So when is it correct that in the isomorphism problem, every vertex of the left graph should be mapped to the unique vertex?
Right, yes. Good? Things are prohibited. So how would we solve such a problem? Like ideally, I would just like to say that I'm reducing list homomorphism like this to the homomorphism problem without any lists. Ideally, I would just like to say that I'm reducing it to such a homomorphism instance, where the left-hand side is now a combination of these two graphs, and the right-hand side graph is the original like host graph. I would like to say that I'm reducing it to homomorphism instance of this kind, and I would like to say that this triangle must be mapped to this triangle, and then I would automatically have all the least restrictions, because this vertex would never be colored this, would never be mapped to this one, and this vertex would never be mapped to this one. I would love to have a reduction like this, but for this I need to make sure that this triangle is mapped to this triangle. And moreover, I want it to be mapped like correctly. I don't want it to be mapped like this. I want this to be mapped to like red one, this to the green one, because these restrictions matter. Here the order of the vertices matter. For example, I don't want you to rotate this triangle when you are mapping it to here. I won't only be talking about such colorings. And this triangle is correctly mapped to this one. And then all of my least restrictions are taken care of. Make sense? Cool. So in order to have this property that this triangle is mapped correctly to this triangle, I need to be able to introduce like some order on the vertices, because like currently a triangle and a triangle, I can flip it whichever way I want. I want to number the vertices in the graph homomorphism problem. For this we do the following. So we find this graph on 6 vertices with the following property, that each homomorphism from this graph to itself maps Z to the Z. It has a fixed point. Whatever mapping of this graph, like a small graph on 6 vertices you have, it maps Z to Z. That's quite easy to see. For example, we can say the following. So Z is adjacent to all the other vertices. So it cannot be mapped to
His own vertex.
sorry?
It should have its own vertex.
Yeah, it cannot share a vertex with like any of these ones because there is an edge between this and this one. Image of Z and image of any other vertex differ because there is an edge between them. So the only possible bad situation is when Z is mapped to one of these. But the thing is that neighborhoods of all of these vertices are bipartite. For example, neighborhood of this vertex is this, this, and this. Oh, I'm just looking at this restriction. Neighborhood of like, say, yeah, of any vertex is a bipartite. But this 5 cycle is not bipartite. It's a 5 cycle. So assume that Z is mapped to one of these vertices, then non-bipartite cycle must be mapped to a bipartite neighborhood of this vertex, which is impossible. So you can rotate the other vertices, but Z will always be mapped to Z. And now I just, in order to have like order on H vertices, I'm gonna have a bunch of these gadgets connected together, actually like H of them. And this gives me ordering of H vertices, because now if I add this gadget to my left-hand side graph and to the right-hand side graph, then I know for sure that the zeros vertex is mapped to the zeros one. First one is mapped to the first one. And by these two gadgets in the left and right graphs, I can enumerate all vertices in the triangle. So I will never have this problem again, that like the green one is now mapped to the red one. I just enumerate them and make sure that the first one is mapped to the first one. And like just for technical reasons, I will also make sure that this added gadget is mapped, that for example our original graph is not mapped to this auxiliary gadget we just introduced. We just basically blow up each vertex by a huge clique, and we say that these cliques must be mapped to each other, and they can't be mapped to, say, to here.
So to the vertex number, say, 3, you add the gadget consisted of 3 these small graphs.
No, just on top, here on top, I have this huge lines of vertices, which are basically my orderings. And now I can connect like first vertex with like the first one there, first one here with the first one there, yeah. And I blow them up, so there's like auxiliary gadgets, I blow them up so that I know for sure they are mapped to each other, that this one cannot be mapped here.
So you need to connect every such line of gadgets to every vertex of the triangle on the left and on the right.
Almost, yeah. I mean, there are some technical things, but that's the idea. Yeah, this gives you a numbering of these vertices. And once you have a numbering, you can kind of insist that, for example, you know that this vertex will be mapped to this one, then it's easier for you to say that this must be mapped to the red one. Because if, for example, you connect it with the first one, this connect with the first one, then you... There are some technical things
So
which is...
To what Z0 corresponds in this?
Sorry?
Z0 to what corresponds?
You add on top of the things. I can't just do a reduction like here. I showed you there might be a bad situation like this. So I have to add a huge gadget here and a huge gadget here. This gadget preserves ordering. Like it's gonna give me ordering of H vertices. And now it's much easier for me to insist that this one is mapped to here because, yeah, make sense? All right. Yeah. Oh, yeah.
Isn't quadratics blow
That's a very good question. You're right that here I add a clique of size h, and I have h vertices like this, so I add h square vertices. But if you recall, we're proving a lower bound of the form h to the like omega of n. And now, if instead of h you have h squared, this doesn't matter much. It it affects this constant, but our constant is going to be so terrible that it doesn't matter for us. Yeah, so we've seen all steps except for this one, and I'm afraid we don't have time to see it. But it's not that important. This is very technical step. And this series of reduction proofs very strong lower bounds for this. Yeah, that's a very good point. Note that we're not starting from exponential hardness. We're proving super exponential lower bounds. How can we do this? At some point, we have to blow the size up. And this is exactly the step where we're doing this. Here we prove a couple of structural results about graphs of bounded maximum degree and embed them carefully into least homomorphism problem. Yeah, but we do blow up the size exactly in this step. Just kind of technical, I'm afraid.
So let's say you want tiles or maybe something based on density. So this is the step that you need to improve.
Unfortunately, that's not the only step which we need to. Here, for example. Yeah. Moreover, 3 coloring can be solved much more efficiently than 2 to the n. It can be solved in time 1.3 something to the n. Yeah, so.
There's a weak in this chain. Let's say you can improve the Saturn K coloring or I don't know what. So.
We don't know that coloring, even the chromatic number problem is 2 to the n hard. Oh no, not true. Only focal length we know. Okay, thank you. We'll 25 minutes.